Hi YouTubers, Dave out in Western Pennsylvania, USA. As you may know from our prior uploaded videos, we're working on supercapacitor technology, focusing on various deep eutectic solvents with a typical electrolyte like lithium tetrafluoroborate. We're using a very easily prepared DES, choline chloride urea, in a 1:2 molar ratio. And what we're doing is focusing on studying the graphite samples as prospective electrodes in supercaps. And we are focusing on graphite felt and graphite twine, sometimes called yarn. Let me show you some of it if you're new to this. I'm in my office, I'm not down at school. But this is the commercially available twine. And it can unravel very easily. I think it has very interesting properties from what I'm seeing. It can unravel very easily into almost like a black hair. Can you see that? Some of it. Thin fibrous material, which has a lot of potential versus felt. And what we do, I'll show you first few cycles here. You can see the discharge is starting to smooth out. That would be in the 4th cycle. We are packing dummy, so-called dummy AA's. I like these clear plastic versus the competitive yellow ones. The yellow ones have advantages because there's a connecting wire between the electrode contacts inside of this. But I like these clear ones. I find them easier to work with. So here you can see we have packed one in a cradle with we've packed the fiber, the yarn, the twine, in the dummy AA, and we have it in a cradle, and we have it in a circuit with a 3.7 lithium ion secondary cell. And they in turn are hooked up with my electronic load device. Why are we doing this? Well, this is what we call a dry run. Now, our definition of dry circuit is not the same as that used by an electrical engineer or electronic engineer. We define a dry graphite circuit as one where the graphite is not in contact with any electrolyte. In fact, we didn't even clean it with isopropyl alcohol. We took the commercial sample as is and packed it into the dummy AA. This is a dry run. Incidentally, there's in there 488 milligrams of the unraveled graphite yarn. So that's about how much we can get in there. There's advantage to this because various DESs and ionic liquids, some of the ones with electronic conductivity values, are not cheap. So justification for using such a DES or ionic liquid in terms of the cost. Now, the choline chloride urea is rather cheap and easily prepared. Now, why do we have it in there with a 3.7 lithium ion? Well, that's easy. After this dry run of 100 cycles, we will add to the content of the dummy AA some of the DES and electrolyte lithium tetrafluoroborate. Close it back up and then run a wet circuit. In other words, graphite material now soaked in a DES electrolyte solution. Okay, but why the lithium ion? Well, most of these commercial supercaps that have organic ones are by convention kept at about 2.7 volts for safety reasons. They can leak, they can boil away, they can catch fire, etc. DESs and ionic liquids have a lot going for them in terms of safety and other related physical properties. Well, what we're doing is we're discharging graphite samples with a lithium ion that I bring up to 4.1 volts. Let's show you my chart. Here you can see the parameter settings, and you can see that we are going to run 100 cycles, and we use a constant voltage to charge the lithium ion up to 4.1 volts. And then we top it off with a current down to a cutoff of 0.20 amps. Standard CCV conditions, but we're going up to 4.1 volts. Then we give it a rest period of a minute. Then we discharge, and we're using 750 milliamps for charging and discharging, and a cutoff for the lithium ion, we're using 3.00 volts. A rest period of a minute, and then the cycle continues. Now you can do up to 999 cycles with the eutectic battery electronic load device. We have about 10 or 12 of them at school. They're very competitively priced. I'm getting them, if I recall, about $120 each USD with postage. Make sure you get the EBC model -A10H. The 20H will not allow cycle patterns. It will only allow a single test. You want, of course, the cycle test, and you could do 999. Now, of course, in industry, they might run 500,000 to 1 million cycles of charge-discharge with supercaps, but I'm working with undergraduate students, and there may be home researchers, undergrads, and even graduate students and professional researchers that may want to test out small amounts of various ionic liquids or DESs that are very expensive, but small scale run to see how it holds up for maybe 1,000 cycles. So we're trying to go up and demonstrate that we can run this and bring it up to 4.1 volts versus the 2.7 volts with the e-supercaps, the electrolyte supercaps. Now, if there's water in there, of course, you're going to be down below, you're going to be about 1.1 volts potential, because you don't want the water undergoing electrolysis to produce hydrogen and oxygen gases. So that's our rationale here. How do the graphite samples with various DES electrolyte solutions hold up? And we do scanning electron microscopic examination of the graphite samples. Now, earlier today, I put it away already, I had run a graphite felt sample, dry, for 75 cycles, and the Coulombic ratio for capacity between charge and discharge was a beautiful ratio, just about 1.0. So I was able to do 75 runs with a packed graphite felt sample. And now, of course, we're doing the unraveled twine sample. Now, look carefully at this for the first few cycles up on my monitor. So over on the left was when we first started. And the lithium-ion battery, the cell I'm using, is the same one as yesterday. But you look how the graph starts to smooth out for discharge. Look how rough it is in the beginning. Well, obviously we can attribute this to adjustments of the surface of that graphite twine. Surface area changes, perhaps? Now, when I run the lithium-ion cell itself, we don't see any such display. Now, don't forget to check continuity of the AA with a multimeter. You want to make sure the graphite is contacting the electrodes in there, the contacts. So check your continuity and make certain the graphite is in contact. It's very easy to forget that, and then you wonder why you get the results you do. But I find this very interesting. And I like to share my research via YouTube because I'll be retiring from teaching in June after 40 years, but I'll be staying with my university doing research. But I like to see people involved, and this is a very good project to introduce people to energy storage. Well, thank you for watching, and I will keep you posted with frequent uploads. Let me just check something here. Oh yeah. Yep, look at cycle 4-1, CCV, 0.041 capacity. And then 4.3, the discharge at constant current, 750 milliamps, 0.044. It's smoothing out. Okay, guys, thank you for watching. I'll keep you posted on our progress. Bye for now.